Good afternoon, everyone. So I'm Sandeep Patil. I work with the IBM Storage Labs based out of Pune. Always a pleasure to be at the SDS conference, whether it's in San Jose or whether it's in India. Right? What I'm going to go through today is genomic deployments, how to get right with software-defined storage. Before I really start, I want to acknowledge all my global team members, right? And these are not only the storage guys. I have few people who actually come from our healthcare division because of the topic that we are discussing today. So before I really start, I wanted to know, is there any biology major? Anyone in the room who has a biology major? Good. I think no one is there, but still, I was told by someone, rather my sister who is actually a pediatrician, that whenever an engineer tries to explain biology, he should start with an apology, right? So I wanted to make sure I kind of level set. I'm going to give you some naive examples. So pardon me, and for the video also, if people are going to look at this video, I'm going to give you some naive examples, but the intent here is to drive the message, right? And why we storage people need to know about genomics. So what am I going to go through? Here. So we are going to have genomic introduction. I'm going to give you a very high-level view of what is genomics, right? Why genomics is an emerging market today. I know genomics has been, as Ravi said, it has been in the marketplace for about, almost a decade now, right? Since the first genome was actually analyzed. But why it has started becoming an emerging market now? Understanding genomic sequencing workloads. Now that it has started becoming emerging, I was just speaking with one of our startups in India working on genomic sequencing. It's important for us as storage to understand what is the workload, requirements on the infrastructure. From those workloads, we'll derive the requirement on the infrastructure, the solution approach that me and my team came up with, right? And the solution architecture. The approach is going to then talk about the architecture, and then we are going to talk about some of the performance number of GATK, right? So let's start with what is genomic. So genomic is a branch of biotechnology focusing on genomes, right? Now you will generally ask me, do I need to really know this, right? Beyond as a storage engineer, right? So I was reading a lot of these articles. In fact, some of my team members should be in the room, Sashi and all, we were actually trying to understand, right? Typically what happens is people get married, right? And when you get married, you have children. When you have children, there is a classical debate that happens between a wife and a husband. And obviously, generally the husband loses always the debate, but still there is a classical debate that happens. And the wife says, look at my girl. She's so pretty. She looks like my mom. And the husband says, really? To be honest, she looks like my mom, right? And it's a never-ending debate. If you actually go and analyze and do some genomic sequencing can help solve this debate. You could analyze the genes and then come and it can tell you who does she actually look like, right? So it's actually, I'm trying to drive the point that there is a lot more that genomic can actually do. Right, so let's get into details. So genomic involves applying techniques of genetics and molecular biology to sequence, analyze, or modify the DNA of an organism. What does that mean? Partly I'll try and cover it in later when we talk about the actual sequencing, right? It finds its use in a number of fields, such as diagnostic, personal healthcare, agriculture innovation. And a lot of people actually do DNA analysis of plants to try and get hybrid, bigger mangoes, bigger bananas, and stuff like that, right? So agriculture innovation, forensic science, which a lot of us see movies and we say, DNA analysis kar diya isne, he's the one who's actually been the thief and stuff like that, right? And others. So then what happens when you start peeling the onion and trying to understand what is inside a genome? So a genome, at a very high level, when you peel, okay, there are 23 chromosome pair in a genome, right? So 23 chromosome pair, out of which 22 pair come from your parents. And the 23rd one is actually telling you whether you are a male or a female. It's the X and the Y, right? We'll not go into the details, but the 22 come from your parents. So chromosomes are made of DNA. So if you start peeling the chromosome at a very high level, you're going to find the DNA. Right? After the DNA are these genes, right? And there are about 20,000 genes in a human genome, right? And then inside the gene, there is a protein. And protein has a function to do something, right, in your entire body. So this is the kind of, actually when you start analyzing, this is what genomic, and then what people do is they actually analyze the genes, right, by doing the next generation sequencing. And we'll go through some part of it and how it derives requirement on the storage. So this actually brings me to another quick story that I'll tell you, right? So especially this 23 chromosomes story, right? You inherit from your parents, stuff like that. So what happened is, a few months back, I actually turned 40, right? And coincidentally, I don't know, after 1 week, my right leg started paining. And I started thinking, is this something that happens after 40, right? And I said, no, I mean, it's paining. I went actually to a physician. So physician actually analyzed me. He saw me, everything, and he said, hey, Sandeep, there's nothing wrong with you, but it's paining. Why don't you go to an ortho? So I went to an ortho, did an MRI. The ortho saw everything. He says, there's nothing wrong with you. Why don't you go to a neurophysician? So I went to a neurophysician. So a neurophysician, he analyzed, I think, both my leg and my brain, right? And then he says, hey, Sandeep, there's nothing wrong with your leg, right? He didn't comment about my brain, but he says, there's nothing wrong with your leg, right? And then finally, I went to my manager, Vamsi, a very, very good friend of mine, right? So Vamsi actually got me a medicine, right, from this. And obviously, as a good friend, he wants me to get well soon. And as a manager, he does not want me to work from home, right? So, but being an engineer at heart and also being a level 3 engineer at the start of my career, I wanted to go and do a root cause analysis, but I was not able to. I said, forget it. Then gave me an assignment of figure out the solution storage architecture for genomics. I said, okay, let me start reading genomics, etc. And then I read about these 23 chromosomes. I said, 22 come from parents. I gave a call to my mom and said, Mom, do you have a leg ache? And she said, Sandeep, when I turned 40, my right leg started aching. I said, there you are, right? So this is very relevant story because we'll tell you about precision medicine later on. So now, coming to why we are talking about genomics, right? You have said genomics has been in the marketplace for a while, etc. But why genomics? Why now? Now, this is my theory. Generally, if you're going to start a startup or something, there are the 3 values that you generally look. What is the feasibility, right, of that particular market? Is it going to be goddamn costly or is it doable? Second, value, and third is the investment. So when you look at the feasibility, the key is there is a continuous decrease in cost for genomic analysis, right? So first sequencing of the whole genome was actually done in 2003, cost roughly about $2.7 billion, right? And then today genome sequencing can cost anywhere around 1,000 to 1,500 USD. And I know if you look at the genome sequencers, right, a lot of companies are into this sequencing. Actually, that's a core business, right? They have actually targeted 100 USD for a genome sequence to be done, which is the MRI the story that I told, the MRI cost me $6,000. It's exactly what genome sequence is going to cost, and that's what they are targeting. So that means feasibility of genomic it's becoming feasible. Second, value. Right now, genomic brings in an era of proactive and personalized medicine. It's a potential of a disruption. To give you an analogy, not an analogy, it's a fact. Right? A lot of y'all would, I'm sure all the men will know it. A lot of us would know Angela Jolie, right? Angelina Jolie, the Hollywood actress. So actually, she has contributed in actually giving a push to this particular genomic trend. So she did her genomic DNA analysis, and her mother had actually died at the age of 57, right, through a cancer. And after the analysis, it came down that she has an 87% of breast cancer and about 67% of some other type of cancer. Right? And this was done after genomic analysis, and they They literally said that this is a particular thing that you have inherited from your mother based on the genes, etc. And then she had to go undergo certain personalized therapy, and now the risk is reduced from 87% to 8%. And that has actually given a lot of motivation even in the US market for doing genomic analysis. And once it becomes 100 USD, it's going to be pervasive. For example, I would say, now this is my analogy, again, this is going to be naive, right? Today what happens is, I get a sore throat. You go to any doctor, what you get? Azithromycin, right? Some doctors give you azithromycin of A company, some doctors give you azithromycin of B company. There's a variation of compound. You as a patient, what you say? Arey, azithromycin of A pharmaceutical company suits me well, right? B does not suit me well, right? Whereas the doctor is not really looking at you, he's just trying to see azithromycin and some formula and stuff like that. In general, I'm talking about. What happens, a day would come that you would actually say, okay, my sore throat I need a precision medicine, right? I'm going to go to my diagnostic center. Today you go and give your blood test, you're going to just give your blood sample. By the evening, you're going to get genomic data. It's going to go to your doctor. Your doctor is going to analyze your genomic data and say, you know what, this fellow needs azithromycin of X compound plus Y compound. While azithromycin is there, but this is the variation he needs, and gets you precision medicine. This is where actually the market will tend. That's what I am envisioning, right? So then investment. This is the third main criteria for the market, right? There has been a lot of investment thanks to the government authorities globally, right? So in genomic, especially because it has to do with healthcare. And growth in the market is majorly attributed by government innovation. And this is something I picked from one of the analysts, right? It is growing at a 10% as predicted and become 20 billion market opportunity. So it's a sizable opportunity for a lot of us to chase from infrastructure. So now questions for storage community. Okay, now we give you a brief background of what is genomics. We are here, SDC, all our storage developers, etc. And there's a genomic customer, right? In fact, in the previous session also, if you really saw, there was a healthcare scientific data analysis that was shown as a reference customer, right? So important customers, and customers going to say, hey, I want genomics as an infrastructure guy, come and give me your reference architecture, deploy it or whatever. Solution architecture. As a solution architect, what happens is, as a storage architect, you say, okay, he wants genomics. My company has 5 file storage products and 10 block storage products. What should I position? So then you are in a dilemma, you go to your developer. And you say, developer, there's a genomic thing I want to propose. I think it is file storage. Is that file storage suitable for genomic? And the developer is like staring. He says, you told me to develop NFS, SMB, unified file and object access. I have everything. People say people use it for home directories. Maybe it is suitable for genomics. Then you go, okay, let me go to quality assurance. I hope they have tested it for genomics, etc. You go to the quality assurance guy. You go to the quality assurance guy and you say, hey, boss, I'm going to sell this. This file storage developer is saying he's done everything well. Are you tested for genomics? Can I sell it? And the quality assurance guy is staring at you. Economics? So you know where this is going, right? So then you say, you know what, there is a problem. As an SDC, as a storage fraternity, we need to understand workloads and try and not retrofit solutions, but try and see what are the natural solutions for that particular workload. So then, obviously, the mantra is need to understand the genomic sequencing workload from a storage perspective. This will solve everyone's problem. Customer will be happy. Solution architect will be able to position what he wants, and the developers will be able to see what I can tune, what I need to develop, and the testers can actually test the actual workload. So then, and this is the approach we took, right? So then I'm going to talk about what are the genomic sequencing workloads. So typically you split the sequencing workloads. Whenever I pitch this slide, I pitch it in 2 halves, right? One is for my manager, which has to be a high level, and then one is for one of our developers, which is going to be low level. So I'll first start with the high level, right? So genomic requires significant focus on big data management, right? There's a lot of data that genomic generates. And I'll show you in that in coming slides of what I mean by it, right? So it's a big data management problem. And second is sequencing of genome results in production of large data, which is really high performance savvy. Now, very high level, genomic data analysis requires basically three processes. Sequencers convert physical sample to raw data. What does that mean? At a very naive level, your blood is converted into some raw data that needs to be analyzed. It is like A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D, a long paragraph, right? Then your raw data is put in a sequence corresponding to a genome, right? What this means is there is a sample, not a sample, a reference genome, human genome that is published. It is published. You can go and download a reference human genome. You have to sample that, make sure you align that genome data, and finally you have to run some analytics, understand the analytics, which is where the doctors, physicians come into picture. So what does it require? It requires ease to use and scalable IT infrastructure. This is at a high level, this is what you're going to do. Okay, I'm going to design an IT architecture, it better be scalable. He's going to need that. Owning, managing, accessing petabytes of storage. Because it's not going to be small storage, it's going to, they are saying it's a big data, that means it's going to produce a lot of data. It has to be able to manage petabytes of storage. High throughput batch processing to analyze data, right? So high throughput has to cater to it because it is, I call it, a technical computing workload, right? A lot of people keep saying high performance computing. I think high performance computing is different. In my opinion, this is a technical computing workload. So then, what does this, I'm going to spend a little time on this, right? Because this is what, if I were a storage or a tester, this is the slide that I'll take away from, right? So what does it mean that this particular next generation sequencing, it's a pipeline. The workload is actually a pipeline. And in that pipeline, each and every workflow, each and every process in that pipeline has its own characteristics, right, from the workload. So first you do the sequencing. Do we do the sequencing? No. The sequencing is done by a sequencer, right? And it is going to, whatever, take your blood, do something, do some sequencing, get the raw data, and spit the raw data onto storage, right? So he's going to spit the raw data on storage, and typically you'll say, okay, sequencers, you have Windows or Linux, etc. He's going to require an SMB or NFS module to spit that data into my storage. Then is processing of raw data, right? Now, what is processing of raw data? At a very naive language so that you people appreciate what happens is, it is like you have to collect, childs play jigsaw puzzle, right? You go to your child and say, see, this is a bird, and then you get the jigsaw puzzle and say, look at the bird and fit the jigsaw puzzles, etc. So first you have to collect all the jigsaw puzzle. So that is what is processing raw data. So you're going to collect all the jigsaw puzzle, whatever the sequence is going to throw it, and you're going to process the raw data and say, okay, these are my jigsaw puzzle, right? So that particular stage is CPU intensive. The patterns of write followed by read. So it's write, read. He's understanding, then he's creating a jigsaw puzzle. Understanding, creating a jigsaw puzzle. And puzzle in the sense, those blocks of the puzzles. Predominantly sequential I/O. Very important to understand, because this is going to vary in every stage. Few large file size, GB file size, there are going to be few large size in this. The raw data, the input data is going to be huge, but the output data is going to be few large files. Right? And accessing protocols, it is predominantly POSIX or NFS, period. Right? It is not anything other than POSIX and NFS in most of the deployments. Then comes the stage of genomic alignment. Now, what is genomic alignment? Again, we have collected all the jigsaw puzzle. You have a sample of a bird, and you're going to say, now I have to fit this jigsaw puzzle to form that bird, right? In biotechnology word, you have a sample, a genome sample out there. You have to figure out all the genomes and try and match what you're getting with a human, not a sample, a human reference, right? And human reference is available it's a sample available for everyone to refer at. So genome alignment, memory intensive, write intensive, and write I/O is predominantly sequential I/O, right? Read I/O is random access. So while doing all of this, the process is also doing random access. Few output files, MB to GB files it's creating. In the previous, it was a lot of huge GB files. Here's MB to GB files and access protocols, POSIX and NFS. Believe me, for us to derive all this took a lot of efforts, right? Because we had to really understand, continuously profile the storage workload, run the GATK pipeline, and try and see what's happening and stuff like that, right? And once we figure this out, we'll go to the solution, etc. Then comes variant detection. Now, variant detection is a very important piece. What happens is, now you have actually sampled, and now you're going to see Where is the variation? Where is that bird not matching? The eye is not coming correctly, right? So you're going to do variant detection. Once the variant detection done, it's a very CPU-intensive operation, right? Storage is relatively minimally used. It actually runs in two modes, storage mode and memory mode, but it is CPU-intensive, memory-intensive, mixed sequential and random file access. So here we generally saw that most of the time it is a read workload, right? Read and write I/O to many files and varying file sizes. Some file sizes are in KBs, some are in GBs, and access protocols, again, POSIX and NFS. And then finally is collaboration. That means you have done it, and now you as a parent want to show to everyone, see, this is it, this is what my child has fixed the puzzle, etc. In short, what you have done is you have done the puzzle. I mean, you have actually analyzed and got the variant detection. You have to share it with physicians. They are going to collaborate even across geos. I know the customer I work with, right? He has subsidiaries across the world, and they collaborate on a genome for inferencing and understanding and actually inferencing what is exactly the anomaly in that particular genome, etc. So what is the collaboration workload? Looks like read intensive, multi-region, multi-site, very important to understand, authenticated and secure, right? Metadata support, they use the concept of tagging, right? And access protocol is SMB NFS object, right? And I've seen as hybrid clouds are evolving, object becomes predominant out there. And fast access across WAN, right? You might see what is this, but I have seen many deployments actually ask for WAN optimization in genomics when this data has to be transferred across intercontinents. So this is actually the crux of the workload. So once you understand the workload, now I can go to my QA and say, hey, have you tested this? I can go to my developer saying, hey, have you optimized for this? I as a solution architect say, okay, this is the workload. Let me create a solution architecture. So let's proceed. So need to think, so what did, now after analyzing this, right, we sat on the bench, right? We were agnostic about storage. This is like a study that we did just to understand, right? So, and we said, okay, we need to think end to end. I come from storage, does not mean I have to think of storage. This particular workload is a little different workload. I will need to think end-to-end, which includes compute, network, storage as the building block. I'm not just going to say, take my storage and run. I'll have to actually think it end-to-end, right? So the infrastructure, compute, storage, and network should allow elasticity, scale in, scale out for building blocks similar to Lego blocks. So we try and and I'll tell you why I'm saying that. We try and debate it, saying, hey, should we go with a monolithic approach, or should we make it like a Lego blocks so that people can just build the infrastructure the way they want for the next generation sequencing workload. And then for storage building block, and I'm going to really, while we deep dived on compute and network also, for this forum, I'm going to just get into the storage building block. Right? Need for high performance file storage with multiple access interface, not a typical NAS storage, right? We understood this is not going to be a typical NAS storage that I can sell, which typically was actually built for user home directories. It's a technical computing workload, right? So, okay, so that is something to keep in mind because it's a technical computing workload. So now these are the inferences we took after doing some profiling and benchmarking, and then said, okay, what should be the principles of developing such a solution, right? So we needed elasticity like Lego blocks. And that is where we debated and came up with saying we need to follow the composable infrastructure principle. Now, what does composable infrastructure principle means? For me, it means Lego blocks. Right? Obviously, there's going to be variation in definition about how crisp it is, but at a high level, it is allowing to have compute, storage, network to grow and shrink as they want to suit to the requirement of the NGS pipeline, right? So composable solutions are built in a way that disaggregates the underlying building blocks, and the building blocks here are compute, storage, and network services. Now, this disaggregation, people say, what is composable? You must have heard about disaggregated principles. Composable is the other name for disaggregation, right? So a disaggregated service provides the required granularity, right, allowing the infrastructure that you can slice, dice as per the need, right? And it facilitates ease in deployment with well-defined configuration and tuning. It's very important. You don't just go and say, okay, put compute whatever you want, put in a network whatever you want, and just grow and shrink. You have to have well-defined template for that workload. You're going to say, this is the computing need, you want to increase, this is increased by this much, this is my template, right? So you need to be beyond the obvious here. And genomic workloads benefit from composable principle as they can grow and shrink the building blocks based on the needs. Right? For example, I have these two customers. One is in India, which is like a startup, right? And his needs was completely different, right? And I have another customer, which is probably the biggest genomic deployment, a genomic analyzing company in the world, which is in the Europe, right? And they have a different requirement altogether. So it had to be actually composable, right? And that's where I felt, okay, had I gone with hyper-converged, or had I gone with a monolithic approach, I would have had to then redesign and say, okay, he's a startup, he'll grow someday, but now that, how do I really fit in so that his network requirements, his storage requirements, compute requirements are different because he's just starting it up as opposed to the other guy who's actually full-blown, right? And hence, we very consciously decided for a composable infrastructure principle. So then, for genomics, a composable building block approach, what does it mean? Right? So you have private network service. Now this is how we stacked it. Right? You can really stack it in some slightly different fashion, but this is how we thought based on the NGS workload. We said, okay, let's have storage services, compute services, and private network services. Very important to have this private network services. This is what we discovered, right? And keep the shared network absolutely different for the genomic sequences. If you mix the two, we figured out that the performance is going haywire, right? And you'll see the performance number that we got, right? And to getting it right, even these small things mattered. So high-speed NFS, SMB, and object access in the shared network is what we are going to keep. User logging, where the user actually submits jobs. Users are physicians here, right? They submit jobs of genomics saying, hey, trigger this particular genomic job, and it actually, there's a scheduler also. I've not talked about the scheduler. He schedules the job, and he actually runs it. Compute service is a big business for genomics, right? And that's why you saw, even in the previous session, he was talking about scientific computing. Even I know one of my, the Power brand of IBM talks a lot about genomic computing and how they are the fastest in the world for genomic computing, etc. But I'm tabling the compute services because we are into storage, right, in this discussion. And storage services, scalable storage cluster to store, manage, and access genomic data, right? And I need to conclude, and tell you why we say store, manage, and access genomic data in a storage cluster that is scalable. And then private network services, high-speed data network, and provision to network and service, and provisioning network and service networks, right, as per will and as per demand. The key thing here from network side is it was important for us to segregate the private network services and the shared network services. From storage side, the key was the storage cluster should be scalable, and it's going to be unstructured data. So now, storage services need for high-performance file storage. What we understood, all these jigsaw puzzles that we were talking about, all these genomes, all the data is file data. That means we are going to require a file storage. Then we understood that, this is not a typical NAS storage. It's a technical computing workload. That means we are going to require elements of what people do in high-performance computing. And that's where we said we need a high-performance clustered file storage. Now you'll say clustered, why clustered? Because we required, if you saw, there was multiple protocols involved. You had NFS data and SMB data where the sequences were ingesting the genomes. Then you had actually the actual alignment, everything happening on the POSIX. You had to share it with object, etc. So you needed one global namespace for these varying workload. It is not a monolithic workload. It's a workload that varies per stage of that pipeline, right? And hence, we concluded that even within, while I have an array of different file offerings, we said we need to go with a clustered file system for this kind of workload. So why clustered? And these are the requirements it helps meet. High performance, high throughput, technical computing workload. Should support scaling and scale out. That's what clustered file system are supposedly designed to do that. Ability to support different kinds of storage at the back end. And that's where the value of software-defined comes into picture. A lot of cluster file systems are generally software-defined by nature. Why is this? Because, again, I told you the example, right? I have a customer who's a startup in India. So it has to support his varying storage needs. So I need to support different class of storage at the back end. Support global namespace. I've already told why the need for supporting global namespace and multi-protocol support. Key. You just have POSIX, not going to help. You just have NFS, You can still work, but are you going to get the performance, right? So you need to have this multi-protocol support. So the key takeaway was taking a software-defined approach and choosing a cluster file system to meet the above requirement. The example in my case was spectrum scale, right? So then, again, I've just given this a snapshot of IBM Spectrum Scale, but it is an example of a clustered file system. What would you need? You need a clustered file system, and you would need SMB, NFS, POSIX, Hadoop and Spark. They also have, a lot of people now are actually analyzing and porting the NGS workload by leveraging Hadoop, so that would be beneficial. OpenStack, Cinder, Swift, maybe Cinder not so much, but Swift, yes, you would need a potential object access if you're going to collaborate, and if the application at the top is actually using object interfaces for collaboration. You need tiering, and as I said, different class of storage. This is going to make sure, I mean, we have had so many talks of multi-tiering. I don't want to sell multi-tiering to you all as to why it is important. It's just important for all kind of workload these days. Multi-site becomes very important, right? I never thought that multi-site is going to be that important until we really worked with these customers and came to know, you know what, a lot of these are actually really multi-region, right? And we should make sure that we have multi-region capabilities, right? And in fact, even tiering to the cloud, because a lot of people are going for a hybrid model where they are saying, you know what, I'm going to run my NGS workload, but you know what, part of it I could even try and do it in cloud. Could be Amazon, could be IBM Cloud, or could be the Google Cloud. And hence you see a lot of these NGS workload even available in these clouds. So storage building blocks, this is what this at a high level it says, you have a data sequencer coming in, you either from the partners or directly from the sequencers. It all resides in the cluster file system, and then you have read and write by physician, read and write by data scientist, analysis of genomic data. This is actually the NGS workload. This is the most important box out here, and then you have to archive that because it's going to generate a lot of data. You cannot afford to rerun the entire workload. Why? Because you'll see how much time it takes in my next slide, right? And then you have to share it and collaborate it with partners as well as your own subsidiaries, etc. So this is a solution architecture. Now, while I talked about the approaches, this is a good architecture for you all to think about, right? What it is showing is, while I have spectrum scale here, what it means is a clustered file system, right? That becomes the crux of it, right? And then it is actually basically showing the entire workflow, right? How the sequencers are actually creating the data, ingesting it. It could be through SMB or NFS. I've seen mostly SMB, right? And then you have these high performance systems, and then you have ILM that goes to tape an object based on the type of data and the age of data, etc. You have to make sure it's the detailed form of the previous workload, right? You have the local data ingest through the sequencers, read and write by physician and data scientists, read and write by Watson. By Watson, what I mean is a lot of cognitive, a lot of deep learning has now started complementing the traditional analytics. And that also started generating a different kind of workload on the storage because they need to read and pump in the data. And then you have compute services. This is a very important one when you actually process the genomic application. That's the pipeline that I was talking about. So this was a quick architecture. I mean, this could be a long session that we can discuss on what are each elements of the architecture, etc. But at a crux, you understood from the storage level what is really required. And now you said, okay, we did all of this, right? What are the performance numbers, right? Very important to understand. I first generated y'all the workload. So the developer is happy. The solution architect is happy because he understands the workload and knows how to size it and how to pitch it. And our quality assurance engineers are happy because they now know and will be more confident of how to basically test systems for this. Now as a customer or as a solution architect, end of the day, you'll say, someone actually gave a very good presentation where they said how the trend is moving from $ per GB to $ per IOPS, right? So it's all about performance also these days. So then we actually did some performance benchmarking. What we did is we actually downloaded a GATK. What is a GATK? It is a genomic analytic toolkit available by Broad Institute, right? Broad is an institute, and it's free for everyone to download it. IBM has it on its website, Google has it on its website, you can actually download it. Then you have to understand how to actually run this NGS. Then you need a sample genome, you got a sample genome, it's published openly. We needed, reference genome, not a sample genome, reference genome. We needed a sample genome. We worked with our customers, got an under NDA and sample genome, and then actually executed the entire pipeline. When we executed the entire pipeline, just to explain you what is this BWA to MEM, this is what was actually making the raw data happen, creating the puzzles. SAM to BAM, trying to match, it's the alignment, trying to match the puzzles to the ideal photo. And these three are the internals of variant detection, right? I'm not going to go into details of it, it's more to do with biotechnology, but you can assume that these are internal sub-workloads of variant detection. And the final outcome is actually the analysis that the physician is going to use. You see this BWA to MEM took 303 minutes, 47 seconds after all the optimization. If you don't do the optimization, we have seen BWA MEM, it goes for more than 2 to 3 days. The entire process of one genome sample takes 7 days, 8 days. Right? If you screw up on the architecture, it's just going to take too much longer. And this is one sample. Just imagine when you have to process 1,000 people sample together, what kind of infrastructure. So this is an optimized number that we have got. Right? SAM to BAM, we could achieve it in 35 minutes, 53 seconds. And the entire thing, the entire variant detection, we have just divided into baseline recalibrator, GATK, print reads, etc. So 87 minutes, 21 seconds, 97 minutes, 1 second, 261 minutes, 37 seconds, and 0 minutes, 51 seconds. Right? While this becomes a very easy conversation when you actually go to a biotechnology company who wants to buy it and say, hey, you know what? While I understand the workload, this is the number you're going to get. With this kind of reference, obviously you can optimize it to get a better number also. This is just a reference based on the systems that we had available and stuff like that, and becomes an easy, easy conversation with the biotechnology company, because all they care is ease of management and are you giving me the numbers. Right? And and why the idea of flashing these numbers, because you come to know how much intensive these operations are. It is not like a simple, very simplistic, it's a technical computing workload. So with this, I think these are some of the references that I have referred to, right? The first one is to do with Broad Institute. Then I did author one of the papers which we have published, which talks about all that I described in more detail, right, of how you can go about it, and some other things around this one. So with this, I'm ready to take any question. But before I take question, I just wanted to tell you, I have one backup slide, which is, as per me, a very good slide. If you are in a storage or this is going to give you absolute details of what we have done with the memory, what we have done with the CPU use to get those kind of numbers. Right? So it actually has divided what were the CPU requirements, what was the main memory requirements. As I said, it was not only about storage, it is about having a composable infrastructure for compute, network, and storage. And this is what will give you the entire details of it. While you'll have my slides, it's also in the reference red paper that I've written. So I'm ready for any questions.
Hi Sandeep, this is very interesting topics. That slide you mentioned that while you're starting the processing of the data, you need to access the multi-geo, some other portion of the data of that multi-geo. So it is a real time, or we can, before starting the data, we can collect the multi-geo required data and then start the process.
Okay, good. So I think, do we require multi-region and multi-location? If the question is, is the requirement of having multi-region, multi-geo during the actual processing of the data?
Yes.
No. So that potentially is either you do it pre, or you have to do it during the collaboration stage. Okay. During the actual sequencing stage, you need all the data there that you want to analyze. So the answer is no. I mean, you need it either pre or either post.
Okay.
So I think your understanding was correct. You don't need it during the process.
Yeah, not required. Okay.
So thank you, everyone. I appreciate your patience.